All right, after a couple of examples for capacitor, let's move on now to inductor to talk about the same back and forth translation between current and the voltage. Okay, so example 3, the given current of inductor waveform and looking for the waveform for the voltage across it. Okay, and also looking for energy stored at one particular time moment. Okay, inductance, keep in mind 10 millihenry. Let's see how we do it. So here I'm repeating the given current waveform. So obviously 3 divisions again, from 0 to 2 with this straight line, and from 2 to 4 another straight line, and beyond 4 is 0. So we obviously can ignore this third division because everything gonna be 0. Okay, we just talk about time windows of 0 to 2 and 2 to 4. Okay. From 0 to 2, again, very straightforward, straight line like this. And it takes 2 milliseconds, be careful, milliseconds. The current change from 0 to 20 milliampere. Okay. So 20 milli divided by 2 milliseconds equals to positive 10 as the slope. So 10t is the current expression between 0 and 2 milliseconds. Okay, and then between 2 and 4 milliseconds, we have straight line downwards like this. Quite similar to example 1. Okay, we need 2 points to calculate this expression of this straight line. Okay, 2 points, we can choose the point here who has coordinates of 2 milli and 20 milli. And second point here with coordinates of 4 milli and 0. So we substitute 2 coordinates into a assumed current expression like this. We can find a constant value A and B. Okay. Specifically, here's the solution. Substitute 20 milli here and 2 millisecond here as the first equation, and substitute 0 here and 4 milli here as the second equation. So 2 equations, 2 unknowns. Find A and B constant. So we know the expression of current between 2 and 4 milliseconds is -10t plus 40 milli. So with the expression of I, we are go ahead to find the voltage, which is equals to the inductance times derivative of the I with respect to time t. So to the first division, I equals 10t, then the voltage correspondingly equals to inductance L times derivative of 10t with respect to t, which is equals to 10. Okay, so after a little bit of algebra, it turned out to be 0.1 volt between 0 and 2 milliseconds. To second division, I equals -10t plus 40 milli. So we are remaining applying inductance times derivative of I with respect to t. Derivative of this guy is equals to -10. So after a little algebra, turned out to be 90.1 volts between 2 and 4 milliseconds. So both are very easy constant values, so you can imagine the voltage waveform is just a 2 flat line parallel with the x-axis like this. Okay? Between 0 and 2 you have positive constant 0.1. Between 2 and 4 you have negative constant negative 0.1, and that's it. After here everything is 0. Last, looking for the energy at t equals to 2 milliseconds. So the formula is half inductance times the current at 2 milliseconds squared. So the current at 2 milliseconds, what is the value then? It's not out of here, since this is a voltage. So it's out of here. At 2 milliseconds, the current value is 20 milli. So substitute I by 20 milliampere. You end up with 2 microjoule as energy stored. Now let's see the other way around. From given voltage waveform, looking for the current of the inductor. Okay, so we can see the given voltage has quite a bit time windows, but luckily most of them are constant values. Very nice. Okay, so this time 0.1 Henry inductor. Okay, and time unit is a millisecond. Okay, let's see the solution. So here, obviously, the first time division is from 0 to 2 milliseconds. Second is 2 to 4, and then 4 to 6, 6 to 9, and after 9 is 0. Okay, so from 0 to 2 milliseconds, this straight line starting from the 0 value, and then end by 10 volts by taking 2 milliseconds, so ending up with 5 kilo times t. This is the 5 kilo rather than 5. Be very careful since we are using 10 divided by 2 milli. This is the first time window voltage expression between 2 and 4, 4 and 6, 6 and 9, we have respectively -5 constant, -10 constant, and -5 constant. And beyond 9 milliseconds, it's just a 0. Okay, so expression of voltage is very straightforward. And then you're thinking of applying the IV relation here. So the current is equals to initial current, again, is involving issue of initial value, plus 1 over inductance times the integral with lower limit for initial time moment and the upper limit of t. Integral of the voltage crossing. Okay, let's see how to do them one by one. So here's the solution for the first time window. Initial value for this time window is the current value at t equals 0. It is either given or otherwise assumed to be 0. And then plus 1 over L 0.1 times integral with lower limit time moment is the initial time moment for this window, which is 0. Upper limit is t. Integral of this v. And then result in 0 plus 25k t squared. This is the current between 0 and 2 milliseconds. To second one, also similar, third, fourth, and fifth. What do we do? Initial value of second one is current at t equals to 2 milliseconds. Okay, because the initial moment is 2 milliseconds, which is also the end moment of previous division function. So the initial value here is obtained by substituting t here with 2 milliseconds. 25k times 2 milli squared equals to 0.1. Plus, this is pretty much 10 times the integral of 95. Okay, with lower limits of 2 milli, upper limit t. As said, third, fourth, fifth are pretty much following the same idea. Initial value is the current value at the end of previous current function. Okay, so I of t equals to 4 milliseconds is obtained from previous function here. Same thing here. Initial value at t equals to 6 milliseconds is equals to the value out of here by substituting t here with 6 milliseconds. Okay. Same thing here. All right. And inside of integral, the lower limit is always the starting moment for that particular time window. 4, 6, and 9. 4, 6, and 9. Upper limit, t. Okay, and then the rest of the thing just purely calculus. Okay. Be very careful. The last division here. We know the voltage is 0. However, it cannot be neglected. The reason is very simple. we have initial value here for this division current. So the current is not necessarily 0. Okay? It's not like example 3 in where the given current is 0, then the voltage is derivative of it, which is definitely 0 too, so we can neglect it. Here, we can't. So now what matters is how to plot the curve, and here is the solution. So to the first division between 0 and 2 milliseconds, parabolic facing up, so we choose t equals 0 and t equals to 2 milliseconds, and then connecting them with a curly waveform, and that's it. Okay, parabolic. Second division, straight line and negative slope, so it's going downwards. We also pick 2 points. One is t equals 2 milliseconds, another is t equals to 4 milliseconds. So the beginning moment and ending moment determining 2 different points, and straight line in between connecting 2 points. That's it. Third one, similarly, choosing starting moment 4 milli, ending moment 6 milli, and we ending up with 2 points as well. Straight line again. Fourth one, 6 milli, 9 milli, giving you 2 points here and here. Okay, so this is the fourth one. Last one, we see the integral is 0. Okay. However, like I said, initial value is not necessary. Turn out to be negative 0.35, constant flat line, parallel with the x-axis. Okay, so this is the current waveform.